let's see, we started talking about the most important notion in probability theory and statistics, which is the notion of random variable. Two types of random variables, discrete and continuous, dependent on the set of values that it takes. A set of values in R, is it a discrete set, so finite or countably infinite, or is it an interval, a continuous one? We've already discussed the discrete random variables, PDF and CDF. These are two functions that are associated with every random variable, whether discrete or continuous. PDF is what describes it, what maybe defines it even. CDF is what helps us compute probabilities about a random variable. And then we looked at families, common distributions, discrete distributions. Most of them referring to or coming from the corresponding model, probabilistic model with the same name, but not all of them. Remember, Poisson distribution has nothing to do with the Poisson model, but it is a very important distribution. Now we're continuing with random variables by looking at continuous random variables. And again, everything about them, PDF, we're going to have a PDF here also to describe it. CDF relationships, we're going to make analogies. What is the same or similar to the discrete case? What is different? There are some differences, notable differences between the two. Okay, so let's recall, we're still in the setup of a probability space, and a general random variable is a function defined on the sample space of some experiment taking real values, satisfying the following property: the event that the random variable is less than or equal to a real number, which to write it as an event is a subset of S. This belongs to K. That structure that was defined to contain all the events on which a probability is well defined. And remember, the reason for that was so that actually we can talk about the probability of this event, because for every random variable, again, discrete or continuous, so a general one, the cumulative distribution function is defined as a function from R to R, defined by that very probability, the probability that random variable is less than or equal to x, little x, the argument of the CDF. In short, we call it CDF, cumulative distribution function. Okay, now a random variable is of continuous type if the set of values is an interval in R, right? So not a discrete one, not a finite one where we can list all the values, not an countable infinite one where we can list a rule for all the values, but an actual interval, possibly the entire R or some other infinite interval. For a continuous random variable with CDF capital F, again, this is defined for any random variable, the CDF is now absolutely continuous. What that means, it means that there exists a function denoted by lowercase f from R to R, such that we have this relationship between the two, such that the CDF can be expressed as an integral from minus infinity to x of that little f of t dt. Remember, the name cumulative distribution function came from the fact that in the discrete case, a computational formula, this is the definition, but how to actually compute it, was the sum of those values of the random variable. So those xi's that were less than or equal to x. So we summed up all the PDFs up to x. Now we're integrating everything. This will be the PDF up to x. And in general, this will be the analogy. Whatever is defined with, or whenever we use sums for the discrete case, that sum or those sums will become integrals in the continuous case. So this function, little f, is called the probability density function, still PDF of x. And this will be defined like an actual function. What I mean by that, in the discrete case, we did that array, values, probabilities, because it was a discrete set of values. We can no longer do that in the continuous case. We're just going to write, f of x equals, as a function, a true function from R to R. Now, a little bit about the terminology. We use PDF to describe a random variable of whatever type, discrete or continuous. We called it probability distribution function for discrete random variables. Now we call it probability density function for the continuous case. This is just because, the two words sort of imply, distribution implies something discrete, where you can actually see each value, whereas density implies something continuous, like an interval. You cannot actually list or see each value, right? So in that sense, it's a natural extension of the word distribution, right? Where we have distribution, we have summation, for instance, for the computation of the CDF, where we have density, we replace that by integration, again, for instance, for the CDF. Now, you have to know that this distinction is not necessarily done by everybody. Not all books or authors do make that distinction. Some of them, in some books, all of them are called probability distribution functions. In others, all of them are called probability density functions, whether they are of discrete or continuous type. For instance, in MATLAB, you probably saw, or you will see, that they're all called densities. Okay, so it's not absolutely necessary. Anyway, in short, it is PDF. Just know that you may find them under both names, and this is the reason why. Okay, so let's explore a little further the relationship between these two, and from what is known about the CDF to derive some properties of the PDF in the continuous case. So I put it in lowercase letters here, just to remind us the properties of a CDF. This was discussed last time. It was theorem 2.4. The fact that it is indeed used for probabilities, to compute probabilities for a random variable. I mean, the very definition is a probability, but there are more probabilities that can be computed with the aid of the CDF. For instance, the probability that x is in an interval on the real line. Of course, when talking about discrete random variables, we have to be careful what type of interval, where is it open and where is it closed. So it has to be open at A and closed at B. The fact that it's monotonely increasing, right continuous, so the value coming from the right is the value at the function, not the one from the left, the limit from the left. The end behavior, the behavior at the ends, at the limits of the interval, so minus and plus infinity, and then how to compute, like I said, other probabilities for a random variable, where we have strict inequality, where we have equality. Using the relationship between the PDF and the CDF, again, these were general properties of the CDF of any random variable, not just the discrete case. So using now the relationship with the PDF, we can derive properties of the PDF, the density function for a continuous random variable. And please note these are standard notation. So for any random variable, capital F denotes the CDF, lowercase f denotes the PDF. We have the following properties. The derivative of the CDF is the PDF. PDF is always a non-negative value. I mean, it does correspond to those PIs in the PDF of a discrete random variables, right? They now describe density of probability. Obviously, it should be something non-negative. The total integral of the PDF is equal to 1. So total on the entire domain. And again, remember that this corresponds to the fact that for discrete random variables, the sum of all the PDFs, the sum of all probabilities on that second row of the PDF was equal to 1. Again, the sum becomes an integral. So total integral is equal to 1. And major and important difference is how to compute probabilities. First of all, the probability that X takes a single value is 0 in the continuous case. This may seem a little weird at the beginning, but remember, we're talking about something that varies continuously. For such quantities that vary continuously, you can never pinpoint an exact value because it does vary continuously. Like time, you know, if I ask you what time is it now, by the time you tell me, that's no longer the real time because time varies continuously. You can never actually say the exact time. That's the same thing here. So for continuous random variables, we can only talk about probabilities that X is in some interval of real numbers, okay, not single values. For that reason, it will no longer matter what type of interval we are considering. Open, closed, half open, half closed on each side. It doesn't matter. The only difference between all these intervals is a single value, or possibly both n values, right? Which actually make no difference at all, that probability being 0. So all these probabilities are now equal, and they are equal to the integral from a to b of the density function. Now, some of these follow directly from the definition of the CDF. For instance, the first one, right? If we look at the way this little f appeared, right? Capital F is the integral of little f. Well, then little f will be the opposite operation of integration, which is derivative of capital F. So we simply differentiate that that relationship to get the first property. For the second property, again, one of the properties of the CDF was that it was increasing, not strictly monotonely increasing, right? A strictly less than B was f of A less than or equal to f of B, okay? Still monotonely increasing, which means that its derivative is greater than or equal to 0, non-negative. But its derivative is the density function. For part C, the limit of the CDF at infinity is equal to 1. But now the CDF is expressed as the integral of the PDF, right? So the total integral is the limit as x goes to infinity of this CDF, right? So the limit at infinity of capital F of x, which we know it is equal to 1. Again, both this property and its equivalent in the discrete case come from the fact that this represents the probability of the Shor event. Okay, so that has to be equal to 1. Finally, the last part about the probabilities. For any fixed x in R, the probability that capital X is equal to X, again, one of the properties of the CDF right here, was the difference of the values of the CDF, actually f of x minus the limit from the left of at x of the CDF. But now, for continuous random variables, f is absolutely continuous. Okay, we're not going to dig into that, what exactly that means, you know, in terms of an epsilon delta definition. But anyway, this is even more than being continuous. So now f is a continuous function. It no longer looks like a step function the way it did in the discrete case. It doesn't have those jump discontinuities anymore. It's a smooth graph. That means limit from the left or from the right at every point coincide, and they're equal to the value of the function. Okay, so these two are the same now, hence we get 0. Then obviously all those probabilities are now equal, right? Because, like I said, the only difference between them is a single value. And we use for this one the fact that this probability can be expressed with the CDF, f of b minus f of a, the difference of the values of the CDF at the endpoints. But now the CDF is expressed as an integral from minus infinity to b minus integral from minus infinity to a of the same thing, which is just the integral from a to b. So major difference, the fact that now the CDF is continuous everywhere. Okay, all of these probabilities are equal. They're all equal with this integral, and we will see another effect of that, which will be used later on, is that now we can see each such probability as an area. Remember, an integral of a non-negative function, a function whose graph is above the x-axis, represents the area of a region, the region that is between the graph of f and the x-axis, in between these values, a and b, those vertical values a and b. So obviously it doesn't matter if we include those endpoints or not. Right? That area is still going to be the same thing. Again, we're looking at common families of continuous distributions, just like we did with the discrete ones. Now, there's a lot more continuous distributions than discrete ones. They are not so obvious. We will see at the seminar many examples. They're not quite so obvious as the discrete ones, where you describe an experiment and you say, let x denote the number of something. That's obviously a discrete distribution, and you can grasp it right away from that experiment. These continuous distributions are a little bit more subtle, however, very useful. We start with the easiest one, the uniform distribution. Not only the easiest one in terms of, you know, formulas for the PDF, the CDF, but it's the only one, remember, that has both cases. We have a discrete uniform distribution, now we have a continuous uniform distribution. It's basically the same idea implemented, let's say, in a discrete manner versus a continuous manner, which will help us understand, you know, the difference between a discrete and a continuous random variable. Again, we describe any variable by given the PDF, and remember, the PDF is defined everywhere in on R. Okay, it's just that if on some parts it's 0, sometimes you may see it written in short, just the part that's non-zero. Like for the uniform distribution, you may see the PDF 1 over b minus a on the interval ab, and that's it. That doesn't mean that it's not defined outside the interval ab. It is always defined everywhere on the entire R. It's just sometimes we omit the part where it's 0 because that part isn't interesting, doesn't tell us anything. So a constant, which constant? 1 over the length of the interval on that interval, 0 outside of it. The CDF, which is now computed as an integral, because this has such a simple expression, this is quite easily to compute as well. We're going to get 0 to the left of A, 1 to the right of B, and this linear function inside the interval AB. Now, I was careful where I wrote equality here, but it doesn't really matter because, like I mentioned earlier, this is a continuous function now. Okay, let's look at the graphs. The density, the PDF, and the CDF. So outside the interval AB, 0. Basically, we're not interested in that part. It's a uniform distribution. Distribute the probability uniformly on an interval. Remember that was exactly the idea for the discrete uniform distribution. We distributed the probability uniformly on a discrete set of numbers in R. A discrete set was from 1 to n. Okay, and again, the PDF there, the corresponding probability was a constant. It was 1 over m. So basically it's 1 over what? 1 over, in some sense, that the measure of that set on which we distribute the probability uniformly. In the discrete case, you know, the measure of a discrete set is the cardinality, the number of elements. Right? There were the numbers from 1 to m that consisted of m elements, so m was the measure of that set. Here we're talking about an interval, right, distributed uniformly, so the same PDF, a constant, on this interval, 1 over the measure of that set. Now this is a continuous measure, the measure of an interval, the length of that interval. Why 1 over that? Because of this property, the total integral here has to be equal to 1, or the total sum in the discrete case has to be equal to 1, you know, corresponding to the probability of the Shor event. And like I mentioned earlier, this probability in the continuous case can be represented as an area. What would that area be in this case? So the area between the x-axis, f, the PDF, between the values of a and b. Okay. So that area should be equal to 1, right? I mean, the total area from minus infinity to infinity is equal to 1, but obviously that area is 0 outside the interval. So the area becomes the area of this rectangle, whose base is the length of the interval AB, so b minus a. Well, then its height should be 1 over b minus a, so that the entire area is equal to 1. But other than that, like I said, area, or, you know, number of elements, the idea is the same. 1 over the measure of the set on which we want a uniform distribution. And actually, that idea can be taken further. We already mentioned vectors, two-dimensional vectors. We also have vectors in the continuous case, two-dimensional or higher dimensional. The idea will be the same, you know, distribute the distribution uniformly on a set in plane, on a circle, or on a rectangle, or an ellipse, you know, two-dimensional vector. The idea will be the same. 1 over, then it will be the area. That's the measure of that set in R2. In R3, three-dimensional vector, 1 over the volume of that set in R3, where we want a uniform distribution. Okay, so that's the PDF, and then the CDF here, like I said, it's no longer discontinuous. So constant 0 up to A, constant 1 from B, and in between the interval AB, it's this linear function. So the graph is a straight line. It's the line segment that joins the 2 points. Okay. It is continuous. We no longer have jump discontinuities, and it's pretty smooth, except at these 2 points, you know, the derivative does not exist. In general, the CDF of a continuous random variable will even be smooth. You know, there will be no problems, no rough or sharp edges like in this case, but anyway, at least continuous. Okay, when does this appear? Like I said, these are not quite so obvious as the discrete ones. So this is used whenever a variable can take any value in a given interval, equally probable. Locations of syntax errors in a program, birthdays throughout a year. A bird, you know, that it is said that this was an example in the book, that if a bird has a magnet attached to its leg, you know, there's some magnetic field or something, it completely loses its sense of orientation. So then it's just as likely that it would fly in any direction. Again, and that would be a uniform distribution, you know, on the interval 0, 2 pi or 0, 180 degrees, because any direction is equally possible. Remember that problem at the seminar, you know, with the spyware, cracking your password, and we determined that, you know, it was possible to discover our password anywhere between now and 7 years. Again, that was a uniform distribution, equally likely any value inside an interval. Very important special case, standard uniform. So see, the parameters are A and B, and this is why it cannot be confused with the discrete one. There was only one parameter in the discrete case, that M. There are 2 parameters here, any real numbers as long as A is less than B. So we're talking about the interval AB. And by the way, again, what you see here in a box is the MATLAB command. So the 2 parameters A and B, A less than B, when they take the values 0 and 1, that's called a standard uniform distribution. Of course, the PDF and the CDF are accordingly simplified, very simple formulas, 1 on the interval, 0 on the interval, 0, 1, 0 outside. CDF, that linear function becomes simply x. These are very important variables, standard uniform ones in stochastic modeling, simulation of random variables, of random phenomena in general. It turns out that any random variable with any distribution, discrete or continuous, can be generated from standard uniform variables. That's a pretty powerful thing. By far, the most important one, the most important continuous distribution in the sense of the applications that it has, is the normal distribution. Many, as we will see, we will use it a lot, many statistical methods use the normal distribution. So a little bit of history here. First described in the late 1700s by de Moivre, you've heard of him with those relations, as a limiting case for the binomial distribution. Actually, there are some very interesting relationships between some of these distributions, including between discrete and continuous ones. For instance, the binomial distribution, when n, the number of trials, becomes very large, but p is small, so that np is a constant, then this approaches the normal distribution. So that was the first time, the first documented appearance of this. Didn't get much attention though, but half a century later, both Laplace and Gauss, independently of each other, because you know they can email each other about their work, rediscovered it in conjunction with the behavior of errors in astronomical measurements, which is why it is sometimes referred to as the Gaussian distribution. So normal or Gaussian are the same thing. Two parameters, and these are standard notation, so you'll have to get used to them. You know, you can't call them A, B, or MN. Mu and sigma in that order. Mu can take any real value, sigma any positive real values, and the PDF is given by this expression here, and this is for every x in R. There's a constant here. The constant is mainly so that the total integral will be equal to 1. The main part is this exponential function. Exponential function with a negative exponent. And in fact, this is what the graph looks like. And I'm sure you've seen this before. Gauss's bell, known as Gauss's bell or Gauss's bell curve function. It's asymmetric. So first of all, it's a bounded graph, both at minus and at plus infinity. This approaches 0. So see, we don't have that part where we say 0 everywhere else. You know, it's a limiting case. Other than that, it's symmetric about the value of its first parameter, mu, which is the only 0 of the derivative. We can see right away that happens. And then the zeros of the second derivative are mu minus and mu plus sigma. This is where the graph changes concavity, right? Concave up and down, or concave and convex. So this is what the graph of the PDF looks like. And see, this is what for any, like we saw for the uniform one before, the entire area under the graph of the PDF is equal to 1. That's that total integral from minus infinity to infinity of the PDF. That means the entire area, the total area equal to 1. Of course, here, since we have the symmetry about mu, we can say that half of this area is going to be 1 over 2, either half, you know, the one to the left or the one to the right. CDF, the integral of the PDF. This again is a known function, has been studied a lot. Such integrals, you know, although they are improper integrals, they are convergent. And the graph looks like this. So we recognize some of the properties we knew any CDF has, like it starts at 0, it ends up being 1, all the values between 0 and 1, obviously, since it's a probability. Notice that now it is strictly increasing, or at least on some part of the domain. Okay, if we drop this case where it's a constant 0, constant 1, at least on some part of the domain, it is strictly increasing. Not only continuous, but strictly increasing. That makes a lot of difference. When it's strictly increasing, that means it's injective. So if we properly take the codomain, we're going to end up with a bijective function, the inverse of the CDF being a very important thing. Okay, so here are all the comments that we made about the graphs of the PDF and the CDF. Why is it called normal? Because it does come up a lot in, you know, applications, in most phenomena. That's the normal way, you know. When it starts to rain, it starts slowly, you know, then and it intensifies and it gets to a maximum where it pours, and then it starts to slow down at pretty much the same rate. People coming to a restaurant at lunch or dinner time, you know, few people, then more and more, then it's packed, you know, you can't find a table, then fewer and fewer, again at the same rate. So a lot of phenomena are modeled by this type of graph. Of course, in real life, none of them are that smooth, so exactly like this. You know, they have little variations, but it's like if you look at it from far enough, you know, from far away, this is the shape that you will see. So that's why called the normal distribution, and like I said, many applications as we shall see. Just like the uniform one, this also has an important particular case. See, the two parameters, mu and sigma, can take any real value for the first one and any positive value for the second one. When those values are 0 and 1, that's called the standard or the reduced normal distribution. In general, I don't know why, but again, this is standard notation. In probability theory and in statistics, a variable with a standard normal distribution is denoted by Z, sometimes without even mentioning, simply by the notation. You know, if you see Z, then it's understood that you're talking about a standard normal distribution. So the PDF and CDF of a standard normal distribution, simplified accordingly when the values of the parameters are 0 and 1. Again, the exponential function with a negative exponent, and the CDF is this integral. The function given here is a known function, known as Laplace's function, sometimes called the error function. It may be not from minus infinity, but from 0. That's simply because that part, the integral from minus infinity to 0, is 1 over 2. Okay, so this is the that would be the only part that's variable. So this is a well-studied function. Its values are found in tables or can be computed by most mathematical software nowadays. MATLAB sure can compute it. And this is important because, you know, there is a relationship between the CDF of any normal general distribution and the standard normal. Okay, and this was highlighted here. Right, this is the CDF of any general normal distribution with a simple change of variable. If you're making t minus mu over sigma, the new variable, this part here, we end up with the integral of this function from minus infinity to this part. Okay, so in other words, the general CDF of a random variable is the standard normal CDF at x minus mu over sigma. So since these values are known, these can be found as well. Another important continuous distribution, the exponential distribution. One parameter, which can be anything positive, very simple PDF, lambda e to minus lambda x for positive x, 0 outside. Okay, so this simple exponential function with a negative exponent, of course it decreases at infinity going to 0. The part to the left of 0 is just 0, not very interesting. Again, quite simple to compute the CDF, so simply to integrate this function here, 1 minus e to minus lambda x, again, for x positive, 0 outside of it. It looks like this. Okay. See that same property that I was talking about earlier, you can restrict it. So on some restriction of the domain, you have a strictly increasing function without these n parts that are constant. Let's talk a little bit about the exponential distribution. Why is it important? It models very well time, lifetime of some equipment, waiting time, you know, in a queuing system at a server or something, half time for some radioactive substance, inner arrival time, that's the time between two consecutive arrivals of jobs at a server facility, for instance. Failure time, again, for some component, electronic equipment. Time between rare events, right, which would be an inter-arrival time. And actually, this is very important here, and there's a strong relationship. Remember, we talked about rare events when we discussed the Poisson distribution, which is a discrete random variable. In a sequence of rare events, remember, didn't quite define rare events, just discrete events that are observed in an interval of time, or more generally, in an interval of something that varies continuously. Those are rare events. The number of rare events occurring in a given interval has a Poisson distribution, whereas the time between two consecutive rare events has an exponential distribution. So this relationship between the two. The parameter lambda represents the frequency. Okay, so time between, say, rare events, frequency of rare events, given, and this is important, given as how many per time unit. So time to the power -1. And here's something important to be mentioned. Sometimes in some books, especially in MATLAB, you may see the exponential distribution defined like this: 1 over mu e2 minus 1 over mu x for x positive, whereas we defined it like this. First of all, whether you call the parameter lambda or mu or, you know, whatever, doesn't really matter. The relevance is important. Now, as long as this is a strictly positive value, you know, you can always regard it as being 1 over something. You know, 2e to minus 2x. That 2 is the same as 1 over 2, right? If it's something that's non-zero, you can always see that. So basically, it's not a big difference. There's not a difference at all between these two, right? The mu from here is 1 over lambda from here, or lambda is 1 over mu. It's just a matter of what does the parameter signify. Basically, it's a different interpretation of frequency. Like, you can say 2 per hour, right? Per hour, that means 2 over the time unit. This would be lambda, measured in time units to the power -1. But that's the same as saying 1 every half an hour. So mu will be that half of hour. So the parameter mu is measured in time units. The parameter lambda is measured in time units to the power -1. So it's simply a matter of interpretation of, do you say that this is you know, like 2e to minus 2x, is that an exponential distribution with parameter 2, or is it an exponential distribution with parameter 1 over 2? Okay, that's the only difference. In general, in probability theory, this is preferred because it just makes computations easier, you know, like computing the CDF. In statistics, usually this one is preferred. We will see why later on when we get to statistics. So this is why in MATLAB you see it defined like this, because, you know, it's the statistics toolbox in MATLAB where it is used. But just keep in mind that it's not really a difference. It's just a matter of interpretation of what the parameter is. The exponential distribution is a special case of a more general continuous distribution, which is the gamma distribution. Gamma distribution has two parameters, both of which can take positive values. It is also used to model time, like total time of a multitask scheme. You know, like you have time between two documents that are being printed. That has an exponential distribution. The total time of printing a document, you know, or something that consists of several documents of several pages, that would have a gamma distribution, right? So total time of such a scheme. And in fact, not only is the exponential distribution a particular case for gamma, but we can obtain the gamma distribution as a sum of independent exponential distributions. See, both its parameters have to be strictly positive values. If the first one is an integer, so not only strictly positive, but an integer, that means a natural number, we can see the gamma variable, the gamma distribution, as the sum of that many independent exponential distributions. Right? So, like I said, you know, one documents take this exponential distribution, the next one this exponential, and this exponential. When you add the three of them, you're going to get a gamma distribution for the total time of printing that document. The fact, okay, this should be a comma here, not a point. The fact that this is 1 over lambda versus lambda here comes just from this discussion here, you know, 1 over lambda or lambda. So for the gamma distribution, we consider 1 over lambda. So, like I said, there are a lot more continuous continuous distributions than discrete ones. In statistics, we will mostly use the following four. The normal, basically mostly the standard normal, the so-called student or T distribution. Now here's a funny looking one. This is the Greek letter chi, you know, looks like an X, but a little bit, you know, curvier. Chi-square distribution. The square is part of the notation. You don't have to take any square of anything. So chi-squared in English, chi pătrat în română. Chi pătrat or chi-squared. And then the Fisher or F distribution. And these are the parameters. See, when we see notations like this M or N, these stand for natural numbers. In MATLAB, you will see they call them degrees of freedom, number of degrees of freedom. So they are positive integers. And before we go any further, like I said, there are a lot more continuous distributions than discrete ones. So here's a file with all their PDFs, right? Written in short, like for the uniform, so only the part that's non-negative, right? For the uniform 1 over b minus a for x in AB. Remember, that doesn't mean it is not defined outside of AB. It just means everywhere else it's 0. So uniform, normal, standard normal, gamma distribution that was mentioned earlier. See, defined in terms of this gamma function that was, you know, briefly discussed at the first seminar. You can look it up, you know, this is the definition. And then there are also some properties there. Exponential distribution, particular case for gamma, right? This is the chi-squared, that funny looking, funny sounding distribution, also a particular case for the gamma distribution. So this is much more general. The student or T distribution. Again, we have the gamma function. Now you will not have to memorize these PDFs, okay? I actually will hardly ever use them in what we do. Just know, you know, that they exist and that you can find them here in this file. Okay, beta, Cauchy, not so widely used. Finally, Fisher or F distribution. Okay, so how they are defined, what kind of parameters they have, you know, we're given all the restrictions here. These are always integer, so natural numbers. Here, strictly positive, and so on. So just know that you have this file here. Okay. So only mentioned here the most important ones, you know, with applications, the ones that we will see and work a lot with later on. Okay, I think it'd be a good time for a short break. Okay, 5 minutes break, and then we'll continue with vectors. All right. See you back in 5 minutes. Okay, let's get back. And continue. All right, so these four distributions we will use a lot and talk a lot about in statistics. Now you know where you can find their PDFs and everything. Okay, just like we did in the discrete case, we can move on to several dimensions and define vectors, continuous random vectors. So everything will now be, again, we just talk about the two-dimensional case. Everything, you know, we'll be seeing double. In a probability space, a two-dimensional random vector, this in general now, a function from S to R2 satisfying the condition. Remember, it was exactly the same condition just for one variable. Now we have the same thing for both components, X and Y. X, capital X less than or equal to X, capital Y less than or equal to Y. This event we want to be, we want it to be in K so that its probability is well defined. Why? Because its probability is the cumulative distribution function, joint cumulative distribution function, just to emphasize that it refers to a vector. But anyway, it's a function of two variables now, that probability. Everything we saw, and we just saw them a little while ago, the properties of a CDF in the one-dimensional case very easily and naturally can be given in two dimensions, so for a random vector. Okay, so for instance, since we have them here, the first one was how to use the CDF to compute probabilities. Okay, this was X between A and B, open at A, closed at B. Now we have the same type of thing for both variables, A1, B1, A2, B2. And in the one-dimensional case, it was simply the difference of the CDF at the two endpoints, right? B, f of B minus f of A. Now we have four endpoints, so we're going to consider all the combinations, starting with the right ones, just like before. So f of B1, B2. Then we substitute one at a time the right endpoint with the left endpoint. So B1 and A2, A1 and B2, those are subtracted. Then we substitute both of them, A1 and A2, that will be added. And you can see how this would work for any dimension, you know. The idea will be the same. Start with all endpoints at the right, all right endpoints, then substitute one of them with a left endpoint, subtract those. Then substitute two of them with left endpoints, those are added. So the signs will alternate until in the end all left endpoints are considered, and that will be with plus or minus depending how many dimensions we are talking about. Monotonically increasing, that is still true for each variable. Right continuity, again, in each variable. Now, when it comes to end behavior, right, at plus and minus infinity, those were the two cases in for one dimension. The limit at minus infinity was 0, the limit at plus infinity was 1. Now we have, again, combinations, which go where? If both of them go to infinity, then we get 1. If at least one tends to minus infinity, we get 0. And if only one goes to infinity, then we end up with the CDF of the other variable. So we let one of them go to infinity, we get the CDF for the other component of the vector. Let's just look at some of those. The first ones, you know, this is again computational. Of course, the comma here, right, even in the definition of the CDF, will mean an intersection, right? Even the way we say it, x less than or equal to x and y less than or equal to y. So it will just be a matter of writing, you know, both these events, the intersections, the right way, and quite easily straightforward computation to get that formula. For the end behavior, we can see why is it, let's start with a case at infinity. Okay, if one of them goes to infinity, we pretty much can just dismiss, omit that part. Everything will always be less than infinity, right? So what's left is just the other part, which is the very definition of the CDF. And of course, it's the same the other way around by symmetry. You know, we can omit the first part. Then if both of them go to infinity, we end up, you know, with a limiting case at infinity of the CDF of one random variable, and we know that that is equal to 1. It suffices for just one of the variables to go to minus infinity to make this entire event the impossible event, right? Whatever happens to x, y can never be less than minus infinity, so the entire thing is impossible. Probability of the impossible event 0. Same the other way around. If x goes to minus infinity, then the first part becomes impossible. Okay, as far as relationship between, okay, so first of all, what is a continuous random vector? Again, the set of values is now a continuous subset of R2. In R, so for the one-dimensional case, we set an interval. Here in R2, in plane, we can have a lot more interesting regions, and we will talk about them in a little while. Now, everything now in 2 dimensions, as far as the relationship between the two, the CDF, which is a function of 2 variables, is absolutely continuous, which means there is a function, again, 2-dimensional function with 2 variables, such that the CDF is now the double integral of the PDF, but the same type of integral from minus infinity to the variable. That function little f is now called the joint PDF, or simply the PDF of the vector. Again, it will be obvious that it is PDF of a vector being a function of 2 variables. Other relationships between a PDF, CDF, when we consider the PDFs and CDFs of the 2 components. So with the usual notations, capital F stands for CDF, lowercase f for PDF. Remember, it was that the derivative, the CDF is the integral of the PDF is the derivative of the CDF. The same thing here, only now being functions of 2 variables, we're talking about partial derivatives. Partial derivatives of the CDF with respect to both x and y will be the PDF. PDF, again, non-negative values because it stands for the same thing, you know, probability density. It shows density of probability, so only positive values. Total integral, still equal to 1, still corresponding to the probability of the short event, only now total integral means double integral on R2. And the part, you know, with the probability that x is in some subset of R, you know, like in the one-dimensional case, in R, pretty much that's all the subsets we can have. An interval, maybe a union of interval. In R2, in plane, there's a lot more such regions, like this here is a rectangle where we can have any other types, you know, circles, ellipse, a parabola, hyperbola, half plane. So a lot more such domains. Now, domain, something that is bounded, but generally any region in R squared. The idea will be the same. Probability that the vector belongs to that domain, that region in plane, will be the double integral of the PDF over that. So a lot more interesting applications here. Also, remember, in plane we have other types of coordinates, not just Cartesian ones. Finally, what happens if we only integrate with respect to one of the variables? Total integral again, so integral over R, right? Function of two variables, f of x, y, but we integrate with respect to only one of them. So the result will be a function of the other variable, and that function is the PDF of x only, so of the first component. Same if we integrate with respect to x, we get the PDF of y. Some of them are straightforward computationals, you know, so I didn't think it worthwhile to actually write down the proofs. Straight computations. See here, from the vector, we obtain the PDFs of the components. When obtained this way, they are called marginal densities. Remember, the name marginal actually comes from the discrete case, where we actually find them on the margins of that PDF, which is an array, you know, like a table, adding on each row or on each column, we get them on the margins, but the name still stands in the continuous case. Independence of two random variables, again, very analogous to the discrete case. In the discrete case, it was Pij can be factored as Pi times Qj. You know, the words, the PDF of the vector can be factored as the product of the PDFs of the components. That's exactly what we have in the continuous case, only now we're talking about actual functions here. So this should hold for all elements in the domain, so all pairs in R squared. Now, the next thing we talked about for discrete random vectors was operations with discrete random variables. You know, usual operations, sum, product, quotient, you know, functions. We still have some product, quotient for continuous random variables. However, unfortunately, even though they are simple operations, the formulas are quite difficult, some of them gruesome. So I chose not to mention them. You know, you can find them in my textbook, but we're hardly ever going to use them per se. We will talk about some sums of continuous random variables, but we won't have to actually use those formulas. They are all defined in terms of the PDF of the vector. So even though you're talking about the sum of two random variables, you have to consider the PDF of the vector that contains the two random variables. However, one case, which is a function of continuous random variables, I chose to present, not only because it is important by itself, but it can help us in other situations, not just the one described here. So let's see what this is all about. Basically, we have a continuous random variable whose PDF is known, and some other function g, and we use it to construct a function of x. So to construct another continuous random variable, g of x. If this function g has satisfies some properties, that is strictly monotone, differentiable everywhere, so its derivative exists everywhere, and it is non-zero everywhere, then the PDF of this newly formed continuous random variable is given like this. I know this doesn't look nice at the first glance, but let's break it apart and see that it's not so bad. First of all, if y is in the range of the function g or outside. If it's outside the range, then this is simply 0. So basically this part we don't care about. If it is in the range of g, what do we have here? See, these are quite restrictive conditions. Differentiable, maybe that's okay. Derivative not equal to 0, that's quite restrictive. But the most restrictive one is this being strictly monotone, strictly increasing or strictly decreasing. Now, very few functions satisfy that. Why is that needed? So that we know that an inverse of g exists. You remember, not every function has an inverse. Okay, strictly monotone means injective. Okay, if we restrict the codomain to the range of g, that also becomes surjective. So in that case, it will be a bijection. An inverse exists of g, and we will see why we need that inverse. And this is simply a composition of functions, the PDF of x computed at the inverse of g. Also a composition of functions at the denominator, the derivative computed at the inverse of g. And this is why we need the derivative to be non-zero, so that this can be down at the denominator. We will also look at the proof because, as we will see at the seminar, the way this is proved works even under less restrictive conditions, because like I said, this is quite restrictive. It will work sometimes for less restrictive conditions. So we say here g is strictly monotone. Let's see what happens when it's strictly increasing, and then with very little change, we will get the case where it's strictly decreasing. And here's the main idea. When you want to get the PDF of a continuous random variable, start with the CDF, with the capital F. Why? Two reasons. First of all, we have this very simple definition for the CDF that we can work on later on, like here. We're going further. Secondly, if this is possible to compute up to some point, we'll see we don't even have to have it entirely, a formula for it. Up to the point where we can take its derivative is exactly what we want, which is the PDF. So start with the CDF, with the simple expression, work on it, if possible, up to the point where you can compute the derivative, and then the derivative is the PDF. So in this case, CDF of y, right, the general definition, probability that y is less than or equal to a point, an argument, little y. What does that mean? Y, capital Y, is g of x. And here, at this step, is where the fact that it is invertible is needed. See, this is probability that g of x is somewhere. I want to get to the point where this is a probability about x. X, remember, is given. It's known. Its PDF is known, which means its CDF is known, which means everything about it is known. So at this step here, get from g of x to x. This is where invertibility was needed. Right? G of x less than or equal to y, apply the inverse to get to x, and because g is strictly increasing, g of x less than or equal to y is the same as x less than or equal to g inverse of y. Okay, when it's decreasing, it's going to be the reverse inequality, and that basically will be the only difference. Why do we want to get to this? Because this is the CDF of x, which again is something known. right? Something given. Of course, this is the interesting part. That's when y is in the range of g. Outside the range of g, if y is less than the smallest value, then this cannot happen. So its probability is 0. If y is greater than the largest value of g, then this always happens. This becomes the sure event probability 1. But inside the range of g, we needed to be able to get from g of x, which is y, to x, right? So to have the CDF of x. And that's it. Now we differentiate because, you know, like I said, we don't need to work on this until we get an actual expression, just up to the point where we can find the derivative. So the derivative of this function, both these last two here, they're constants, so derivative will be 0. So this is anytime y is outside the range of g. Inside here, this is the derivative of a composite function. So that will be the derivative of the outside function, right? F of x prime at the same argument at g inverse times the derivative of the inside function, derivative of g inverse. Now, derivative of capital F of the CDF is the PDF, so computed at g inverse. The derivative of the inverse function is 1 over g prime of g inverse. So we got this formula for the case when g is strictly increasing. Being strictly increasing means its derivative is positive. This is why we didn't need that absolute value at the denominator, right? G prime is positive, so absolute value is just that. When for the case when g is strictly decreasing, we go pretty much the same way. The difference is at this step here, g of x less than or equal to y. When we take the inverse of g on both sides, we're going to get the reverse inequality because g is strictly decreasing, right? A less than b implies g of a greater than g of b. So at this point, it's going to be probability that x is greater than or equal to g inverse, which is still fine because it can still be expressed in terms of the CDF of x. So in terms of the probability of being less than something, right? With the probability of the complementary event. 1 minus the probability that it's less than. It doesn't matter in this case, strictly less than or equal, because we're talking about continuous random variables, and we just saw one single value doesn't make any difference. Okay, we still go further, taking the derivative. We're going to get a minus sign from here when taking the derivative. Everything else looks the same, and that minus sign now put together with the denominator, right? When g is decreasing, its derivative is negative, so that means minus g prime is positive. So minus g prime is the absolute value of g. So we still get this part here. Okay, this in itself is quite a useful result. We'll see examples at the seminar, but more than that, and again, this is the reason we went through the proof here. The way it is proved works for other cases where we cannot use this proposition, so we cannot use directly this result, because the function g will not be especially strictly monotone. The other conditions, you know, are lighter, but being strictly monotone, that's quite something heavy. Very few functions satisfy that. Once again, what's the idea? To start with the CDF of the new variable, write it, if possible, okay, in terms of x. So if this step here is possible, going from g of x less than y to finding some probability for x. Now it doesn't necessarily to be of the same type, you know, less than or something, or greater than or something. It may be an interval, will be sometimes. That's still okay, as long as we can get to a probability for x, because that one can always be expressed with the CDF of f. And at that point, and again, we'll see actual examples, we don't even have to work on, you know, computational, find an exact expression, up to the point where we can find the derivative. So not make unnecessary computations. When we get it to that point, we take the derivative, you know, and that's what we want, because that is just the PDF. Okay, so this is the only case, like I said, as far as functions of random variables, right? Not so much about operations and everything, because, you know, the computations are just too complicated. And once again, don't forget, you know, there's going to be other formula sheets here. You know, for now you have this list of continuous distributions, you know, their PDFs and everything. Okay, that is it for today. If you have any questions or any comments or anything, if you're still alive, you know, if you're not asleep and everything, are you still there? Yeah. Even after a year and a half, I'm still not used to, you know, talking to an empty screen, you know, nobody's saying anything. So, anything at all? Any comments, any questions? All right, then. You have a nice day. I will see you later. Bye-bye.
Goodbye.
Goodbye.
Bye-bye.
Bye.